So it's a pleasure to be here, and I'm going to talk about, I'm an experimental physicist. I do research in particle physics, as John said, and I'm going to talk about what I consider as miracles. Now, if you look in the dictionary, of course, I did, various dictionaries. The Oxford Dictionary, the first one I looked at, has two definitions. And one is an extraordinary and welcome event that is not explicable by natural or scientific laws. It does continue and is therefore attributed to a divine agency. I put a question mark about that because I'm not quite sure as a scientist what that means, but certainly things like the Big Bang was an extraordinary welcome event that is not explicable by natural or scientific laws. The second definition, a remarkable event or development that brings very welcome consequences. Again, many things in physics and in our universe allow us to be here, allow life to be here. And so those we consider welcome consequences. Other dictionaries have similar pairs of definitions. For this talk, what I mean by miracle is very much in line with the first part of that definition. Something amazing that, while not violating established laws of physics, didn't have to be true, but is known to be true and allows us to be here as living conscious beings. Of course, that's quite a deep thing, but and of course, I won't have the final answer, but I hope to give you something to think about. Now, miracles, I don't include some of the miracles written in the Bible, like walking on water and turning water into wine. I would recommend this book called The Sins of Jesus. It's a historical novel written by Richard Muller, who's a physicist. He got a MacArthur Genius Award. And it's Life of Jesus as a historical novel. And in there, you can see how Jesus could have made apparent walking on water and turning water into wine and so on. So that is, as a scientist, an interesting book about the life of Jesus. I do include the masses of particles, the forces between them, and the age of the universe. So these are things that are miraculous in some way. Now, you've heard of the Goldilocks Principle, I suppose. Not too hot, not too cold, but just right. Her porridge in this case. Now, our planet, of course, is not too hot, as some planets may be, or are actually, not too cold. This is actually an artist's impression of the surface of Pluto. And it's methane, it's methane ice there, it's not water ice. And this is, of course, a just right. Actually, this picture, which I, of course, picked off the web, is one representation of the Garden of Eden, but, of course, they're clothes, so that's a particularly child-friendly one. But I'm talking about the Goldilocks Principle applying to the universe as a whole, or universes. We'll come to that. So the brain is the most complex thing in the universe that we know. As far as we know, it's the most complex thing. Maybe there are more complex things, but this is certainly incredibly complex. There are something like 300 billion interconnected neurons. That's 300 billion or 300,000 million. 3 times 10 to the 11, that means 3 with 11 zeros after it. And interestingly, a coincidence, that's roughly the number of stars in a galaxy like our Milky Way. We talk about 100 billion stars in a galaxy like our Milky Way galaxy. And it's about also the number of galaxies in the visible universe. These are big numbers, 100,000 million stars in our galaxy. And we'll see that we think most of them have planets. And the number of galaxies in the visible universe, which is maybe only part of the everything. So going historically, the very first miracle was how the universe came into existence. And we don't, of course, know before that, does everything have to have a cause? Did time itself come into existence when space did? Einstein and Minkowski sort of unified space and time. So it's conceivable that space and time came into existence together. But we know then that since the beginning, the universe has been expanding, galaxies are rushing apart. That was established by Hubble, who actually was from Wheaton, where we are. And he measured the speeds of galaxies and shown that they are rushing apart. The further away they are, the faster they're moving apart. And that gave rise to, there were 2 pictures of the universe at that time. One was called a steady state picture. Fred Hoyle and Tom Gold promoted that picture. They accepted that the universe is expanding, but they thought that maybe it should look the same at all times, roughly, and the same in all places. It's called a perfect cosmological principle. So as it's expanding to keep the density constant, new matter would be created in the void. The other idea was that extrapolating the expansion backwards in time, you get to a time when the universe was tiny, smaller than an atom, in fact, we believe now, much smaller than a proton even, and that's called the Big Bang origin. And this one has become established now by essentially all cosmologists and scientists. And you can actually sort of see this in a way because the proponents of the Big Bang hypothesis predicted that the universe was extremely hot at the beginning, and as it expands, it cools. Like when you expand a gas, it cools. When you compress it, it heats up. And the prediction was that if the universe was really very small in the past, it was also very hot and emitting a glow of X-rays and ultraviolet. But that, as the universe expands, that glow has been cooler and cooler. And at some time of about 380,000 years after the Big Bang, the universe became transparent. Before that time, light couldn't pass through because there were no atoms at that time. There were protons and there were electrons and neutrinos, but the universe was sort of opaque. But at this time, atoms could form, the universe became sort of transparent, and we can look back and see this is a whole sky map. Looking over the whole sky, it's been obviously turned into a sort of a flat disk, but it's the whole sky. And this is the microwave background. It's become microwaves because of the expansion, the stretching of the light, stretching to longer wavelengths, beyond red, beyond infrared to microwaves. And if you have a hot body, emits what's called a black body radiation spectrum. And the spectrum of the microwaves in this microwave sky is given perfectly well by the spectrum of any black body. When you heat it up, heat a poker, it's red. Heat it up more, it becomes white, blue, and so on. This is actually from the Planck spacecraft, which measured. Now, the red and blue spots here are tiny variations in the temperature and also in the density of there. This is a whole sky map. So as the light was emitted at 380,000 years ago, it was in ultraviolet light, very hot. As the universe expanded beyond that, the light was stretched, became visible light, infrared light, heat, and microwaves now. So the patches you see in red and blue, it's amazing. They're a tiny bit warmer in red or cooler in blue than the average, but only by a tiny amount. You see this scale here is 200 microkelvin, that is 0.2 degrees Kelvin. Red minus 0.2 here. Very, very small patches. But the warmer patches became slightly less dense and the cooler patches slightly denser. And the origin of these variations, which seem to come from quantum physics right at the very beginning of the Big Bang, remain even at 380,000 years. And the slightly denser patches condensed more under their own gravity and became galaxies and clusters of galaxies and stars. So the denser patches grew denser and seeded galaxies and galaxy clusters. So this is, now here's a cartoon of a history of the universe. So we now know pretty well the age of the universe from the Big Bang, 13.8 billion years. And this is, of course, is a lot of information on here, but there was a period when the universe seemed to start much, much smaller than a proton, trillions of times smaller, actually. But it exponentially grew until it was something like the size of an orange. It started probably at a Planck time, which is 10 to the minus 43 seconds. And then it grew exponentially, doubling and doubling every trillionth of a second. And then something happened. So I call it whoosh. There was a change, a phase change. And suddenly it stopped expanding so fast, exponentially, and continued expanding smaller. But then this was this incredibly hot thing. And at this point, we believe that matter and antimatter particles came into existence in equal numbers. Before that orange or so sized Big Bang occurred, then the physics is, of course, unclear there. but we don't think that there were certainly no protons or neutrons there, and these came into existence probably at this time. So this is really at the frontier of our understanding of cosmology here. Now, I have to say a few words about matter here, because, and you probably are familiar with this, but an atom has in the central nucleus the protons and neutrons stuck together. And these protons and by the way, the nucleus is really much smaller than an atom. It's in linear dimensions, it's 100,000 times smaller than an atom. So if you magnified an atom to the size of this room, the nucleus would be like a pinhead in the middle of that. Cartoons showing the nucleus as a much bigger thing are just misleading in a way, but we show them like that. So a proton is made of smaller particles called quarks, and there are two types in the nucleus called up and down. I don't have to explain those names, but the proton's got two up quarks with charge 2/3 each, and a one down quark with charge -1/3. You add them up, you get +1 is the electric charge of a proton. The neutron is only different because it has two down quarks and one up quark. Now, I'm coming to something quite important here, because they're very similar in mass, but they're not exactly equal in mass. And of course, these colors are not real. They're just ways physicists have. Three colors make white, and these things have total neutral color. But the quarks cannot escape from they're confined in these protons and neutrons. We've never seen a free quark emerging outside protons and neutrons. So Gell-Mann thought up these ideas of quarks in '64, got a Nobel Prize for that. George Zweig also had the same idea. He called them aces. He didn't get the Nobel Prize. But you and we all made of just three different particles. All atoms, gases, plasmas, and so on, are made at root of up quarks and down quarks and electrons. And then there's a fourth partner to the electron called the neutrino, and they don't form part of matter because they zip through at essentially the speed of light. I'll say a little more about that. But I want to come to this idea of these quarks and see on the next slide. This is just to say how incredibly small these things are, because this is a logarithmic scale of size in meters, okay? And every tick mark is a factor of 10. And 10 to the 0 is 1 meter. A human being, about 2 meters, that's the size of us, roughly, 1 or 2 meters high. And then here's the planet Earth, and here's the diameter of a human hair. That would be a millimeter. This would be 100 microns. Diameter of a human hair. The hydrogen atom is much smaller. It's 10 to the minus 10 meters. And the nucleus, as I said, is 100,000 times smaller than the atom. And electrons and quarks are much smaller still. But if you just look at these lengths here, just think about this. An atomic nucleus is to hair as hair is to Earth. So if you took a ball that just fit in a human hair and magnified it up to the size of the Earth, then the nucleus would be the size of the human hair. I mean, it's really, we see it as a whole other story, but we can actually measure these distances and so on. So here is now a chart of the particles of matter that we know, okay? I've talked about the up quark and down quark that make a pair. And in this family, there's the electron, and these things, as I said, make up normal matter. And there's a neutrino that is like an electron that's lost its electric charge and practically lost its mass. Trillions per second are passing through you. They interact almost not at all. It's very difficult to detect them. You need a very massive detector. But everything's made of these three, basically. So then it was discovered that this family is replicated by a heavier family called the charm and strange quark, and a heavy version of the electron called the muon, and it's got its own neutrino. And then there's a third family still, the top quark and bottom quark, which were discovered at Fermilab. And the tau is a heavier version still of the electron and muon family, and it's got its own neutrino. So these 12 particles, they all have different masses. We don't have a way of calculating those masses. It's mysterious, the spectrum of these things. So no understanding of the spectrum, really. But interestingly, the mass of electrons is the same wherever you create them. And you can create an electron where there wasn't one before. A photon, a particle of light or a gamma ray, can convert to an electron and a positron pair, matter-antimatter pair. And no matter where in the universe this happens, these things arrive with a certain, they know what mass to have somehow. And it doesn't matter where in the universe you are. And there's a theory that explains how these particles have their mass. And this is due to the Higgs field. I'll come to that. But there's several interesting mysteries here. The third family allows matter-antimatter asymmetry. So this is a bit technical, but it seems that theorists, if you only had these two families, then matter and antimatter would be perfectly symmetrical. No reason why our universe should be dominated all by matter and not antimatter. As I said, at the very beginning of inflation, it seems that matter and antimatter were equal amounts, and now we're dominated by matter. We don't have antimatter planets and so on. So it seems that all the antimatter was annihilated at the very beginning, leaving matter. There's a tiny asymmetry there. And the theorists, in fact, some predicted this third family by saying that we have matter-antimatter asymmetry that allows us to be here. And theoretically, that required this third family. And there doesn't seem to be a fourth family like that. We know there's only 3 of these neutrinos. We can measure that number. Of course, all these 12 particles have an antimatter partner exactly the same mass. But those antimatter partners are not around now. So there's the 3 families that allow us to be here, because if you only had 2, and yet these are all unstable particles. These all decay very quickly. So these are the stable ones. These are there, and you might ask, well, why are they there? What's the reason? Is it there because that allows matter to dominate a universe here? So on the next slide here, I show these 2 more miracles. There's 3 families. I'm repeating myself here. The stars, planets, and us, we're all made of these particles in the first family, up quarks, down quarks, and electrons. And then there's 3 neutrinos. They zip through the universe at nearly the speed of light. They're strange. They mix between each other, and Fermilab is studying these and trying to understand the difference between neutrinos and antineutrinos, and maybe that is a clue to the antimatter asymmetry in the universe. And these other 6 matter particles, as I said, charm, strange, top, bottom, muons and tau, they're all unstable and decay very rapidly, less than about a microsecond. So we can see them, their tracks, but they decay very fast. Do they have a role in the universe? Why are they there? Now, physicists, we tend not to ask why questions, but how questions. But here, for this particular purpose, the question, are they there for some reason in order to allow matter-antimatter symmetry? And I put question marks here because it can be made true that a universe, if you had only 2 families, would not be matter-dominated and could be sterile, maybe. And then there's the masses of these matter particles. There are 12 of them. There are the 6 quarks and these 3 so-called leptons, the electron, the muon, and the tau. And how do they get their masses, and what masses do they have? They're all different masses. Now, we don't have an understanding of the pattern, but there's a theory for how they get their masses by interacting with a field called the Higgs field, which is a new field that was, in 1964, thought up by several theorists. And as particles like electrons plow through this field, they acquire mass. And I can't explain in detail why, but the fields that we know and love, like electromagnetism and gravity, those fields have a direction, like gravity pulls us down on the Earth, or the Earth to the sun. Gravity's got a direction, and it's different everywhere you go. Of course, deep in a well or up in the mountain, it's different. The Earth's gravity is different. And electromagnetism, you know very well that near a magnet, you've got a very strong field. Far away, you don't have. But this field, the idea is it's a field that is uniform everywhere, and it doesn't have a direction. It just has a value through space. And when a particle like an electron zips through that space, or the quarks too, they acquire mass. So I'll just say that if that field value were doubled, what it is, I mean, we can measure what it is. If the field was doubled, the electron mass would double. What would that mean? All atoms would be smaller, and the chemistry would be completely different. On the other hand, if the Higgs field value was much smaller, electrons would be much lighter, and atoms would be fragile, or maybe not possible at all, because the lighter the electrons are, they tend to zip off at the speed of light and not be easily constrained to be in an atom, and the field was turned off. If that field was switched off, the electron mass would vanish, so would the quark masses, by the way, and it would zip through space at the speed of light, and that would be a very different universe. So somehow, this is what I call a way in which we can have a universe with complexity of life, with complex atoms and molecules, and it's really due at some level to the field of the Higgs field, and so on. Now, the Higgs was a theoretical prediction, 1964. Several theorists had the idea of this field, but it was Peter Higgs who said, aha, if that field is true, there should be a particle that goes with it, a quantum, like the photon is a quantum of electromagnetism. And so he said there should be a particle that goes with it. Interestingly, the paper he wrote didn't have that prediction in, and it was rejected by the referees. And when he resubmitted it somewhere else, he had this great idea that, oh yes, there should be a particle that goes with it. And he put that in there. Couldn't calculate the mass of the particle, but maybe its properties, it's got zero spin, it's heavy, and so on and so forth. So it was at last discovered with the Large Hadron Collider at CERN on two big projects. This is one called CMS. I am a member of this project. You see it's a huge, like a digital camera in some sense, and collisions occur between protons at extremely high energy inside a beam pipe here, and the Higgs boson can be produced in only one in billions of collisions, but we were able to dig it out of the signal. So that was an amazing thing, very exciting thing, because it sort of confirmed this theory of this Higgs field that goes, that fills the universe and gives these particles their mass. And particles couple to the field according to their mass, but that doesn't mean we calculate those masses yet. So there's 12 numbers in the standard model, the masses of these quarks and these electron-type particles or neutrinos, and we may find a theory that gives that spectrum, but we haven't found it yet. And it's perfectly possible that they're like 12 random numbers, and that in some different universe there'd be different numbers, and physics would all be different. I'll come to that later. So here's another very strange sort of thing, and you may say, well, it's a coincidence, but it's not really it allows us to be here because there's a relationship, the theorists have a relationship between the mass of this top quark that we found at Fermilab, and I was privileged to be part of that discovery as well as this discovery, and these two particles have got a relationship between their masses, and here's a graph showing the top mass here, of 100 GeV, 150 GeV. The proton mass is 1 GeV, roughly, 0.9, and the Higgs mass here. And theoretically, the vacuum, which obviously is stable, the vacuum is stable or we wouldn't be here. But when they put this in the theory, they find that the vacuum could be unstable and decay to a different state if the relationship of these masses was up here. Or here's a region of these masses where the vacuum is stable. We don't have to worry about it. The yellow region, which gets quite narrow up here, you see, is called metastability. What that means is that it's semi-stable, but it could tunnel into a different vacuum state. And we're lying in this region here where the vacuum seems metastable. This down here is a zoomed in version. Here's the Higgs mass between 110 and 140 GeV. This is where we have measured it to be. This is the top quark mass. And this is a region, sort of experimental uncertainty on the measurements, and it lies within this metastable region. If it was up here, then we'd have, it seems, according to these theorists, the vacuum would be unstable. The whole universe would decay into some different state. Now, this seems like a very precarious thing. Of course, I have to say that there's a lot of physics we don't know about the vacuum, and other unknown physics could change this picture. But it's sort of remarkable that the masses of the top quark and the Higgs, that we can't calculate from first principles, but they happen to lie in this region, the yellow region, where the vacuum is precariously stable. It's called metastable. There's a sort of potential here where this is called the false vacuum that we're in, this theory. This is the Higgs potential, and you could have a tunneling into a true vacuum with the lower energy in the vacuum, that would change the whole vacuum. That would change the universe. So it's a very delicate balance that we're in here. Now, let me come to one thing that I think is really very interesting, sort of almost sort of miraculous in a way, which is that neutrons decay. A free neutron decays with an average lifetime of about 14.7 minutes. It's an exponential decay, but this is the mean lifetime. And it decays to a proton, an electron, and a neutrino. Now, it can decay that way because it's slightly heavier than the proton. The mass is, in some units, MeV units, but 939.565. The proton's 938.272, slightly lighter. Now, where does this mass difference comes from? At the deeper quark level, I told you about quarks, and the neutron is 2 down quarks and 1 up quark, and the proton's 2 up quarks and 1 down quark. And in this decay, a down quark in the neutron turns into an up quark, and it can do that because it's slightly heavier. You see, it's only it's a very small percentage heavier. But suppose it was the other way around. We don't know. I mean, it could have been, as far as the physics we know, the other way around. And then, if the proton was heavier than the neutron by the same amount, flip those masses, protons would then decay, and what would be left in some time after the Big Bang would be not protons and electrons and antineutrinos. It would be neutrons and electrons and antineutrinos, and also positrons. But that would not allow hydrogen, because hydrogen needs protons, stable protons and electrons. But if the proton was decaying like the neutron does, with a lifetime of 15 minutes or so, there wouldn't be hydrogen. That would disappear. So our hydrogen, which seems to needed for life, is basically able to happen because the down quark is slightly heavier than the up quark, which seems odd because it's got less electric charge than the up quark. So you might think it would be the other way around. Then another sort of miracle is why is the universe all matter? And again, nobody knows, really. The general belief is that at the very, very beginning, it was neither matter nor antimatter. During this period of exponential growth, inflation, it was balanced. Photons are neither matter nor antimatter, and space is neither. And the particles came into being, and then the general belief is that a tiny asymmetry arose. Like for every billion and 1 matter particles, there was a billion antimatter particles. So 1 part in 10 to the 9 or so difference, a slight asymmetry between matter and antimatter. And then all these billion particles could annihilate with each other and make photons, billions of photons, and leaving 1 matter particle left over. And that is called baryogenesis, and that allows us to have a matter-dominated universe. So our matter has come actually from a tiny, tiny fraction of all the quarks and antiquarks and so on that were there at the beginning. This is our best theory about that. So we don't have a good theory for the tiny asymmetry yet. That means we don't really understand it. And that 10 to the minus 9 is what we believe it to be, but suppose it being 10 to the minus 8 or 10 to the minus 10, this slight asymmetry was bigger or smaller, how different would our universe be? Now, while most cosmologists think that this annihilation happened, it's not really proven yet. I think that is a general belief because in inflation, they think it must have been symmetrical, perfectly symmetrical. There's an alternative possibility. It's not a mainstream one, but it's one that I have written about, that actually the Big Bang was part of a universe-anti-universe pair creation. So the Big Bang we're here in an expanding universe, but at the same time, there was an anti-universe produced with what we would call anti-particles. And particles go around. Time is a closed loop in this idea. Time is a closed loop. And in the very far future of the universe, trillions and trillions of years hence, it will match up with the anti-universe. And that is, but so the big crunch, Big Bang, they're joined up together. Now, it's like an electron-positron loop in our vacuum by quantum fluctuations. I put this out there. I can't resist putting it up there because I like the idea. It means that time doesn't have a beginning or an end. It's a closed loop, and space is too. And there are no infinities and no infinite future. but it's not an established idea. Now, here's another really interesting miracle. So this is the existence of carbon. Where do carbon atoms come from? So our universe originated with this Big Bang, as I said. It wasn't actually big. It was much smaller than a proton at the beginning. But we had these protons and neutrons and electrons there. But then the neutrons, after, on average, 15 minutes, they were decaying. But before they decayed, neutrons and protons could stick together to make deuterium nuclei and emit a photon. And that could then grab another neutron and make hydrogen-3 or tritium, could grab a proton and make helium-4. So in the first seconds, these elements were built up. And this Big Bang so-called nucleosynthesis has been well worked out. And there's a little bit of lithium as well. But after that, the expansion was too fast and it's too dilute. So no heavier elements were made at this time. So where do they come from? Carbon, nitrogen, oxygen. All the heavy elements were not coming from the Big Bang. They were coming from stars. The whole universe was a hot, expanding, and cooling plasma of these free protons and electrons. Okay, and it's opaque. Then, about 380,000 years ago, I said, the universe was cool enough for atoms to form, and the universe became transparent. Light could stream through, and it's okay. Now, I think I certainly believe, maybe we all believe, that life requires complexity. It's hard to define complexity, quantify it, but a gas or plasma is something very simple. It's hard to imagine that it could be some thinking or whatever. It's a simply described system. A diamond is a simply described crystal of carbon atoms. Carbon has got an amazing variety of solid forms. Here's a whole pictures of graphene, coal soot, diamond graphene, nanotubes, buckyballs, and so on. They're all ways carbon atoms can form together to make different forms of carbon, because it has this remarkable property of having 4 electrons in the second shell, and it would like to have 8. So it's got like 4, it's called 4 valences. So this can easily couple to other carbon atoms in these forms. This sketch, by the way, I just want to say that it's misleading in a way, because it's just a cartoon. The nucleus of carbon, which is 6 protons and 6 neutrons, is actually tiny, as I said, compared with the atom. It's 100,000 times smaller. And the electrons aren't really points, they're waves waving around and so on. But anyway, the second shell can have 8 electrons from this quantum mechanical thing. So 4 more is okay. So you can add 4 hydrogen atoms around there, and get methane, for example, and then methanol, ethane, ethanol. So you can easily build up with this property of carbon, quadrivalence. 4 is valence of 4. It can have 4 hydrogen atoms joined to it, and then build up very more complex things. So here's an example of pyridine-3 carboxylic acid and so on. But we'll go to much more complex things. And only carbon, of all the elements, seems to be able to do this, joining with hydrogen, oxygen. Now, you can say, well, what about silicon-based life? Silicon is also tetravalent, but it's quite, and you can make silicon H4, or silane, it's a repulsive smelling toxic gas, and you can make silicon polymers, like these things, but no rich complex molecules. DNA and RNA type molecules based on silicon rather than carbon seem not to be able to exist. So carbon seems to be really very important for life, for complexity. And it's the only element, just the right structure. And here's just a tiny section of a DNA molecule, you know, the double helix. And these are the other atoms that there in this molecule of life here. It's not just hydrogen and carbon, but you have oxygen, nitrogen, phosphorus, and so on. But carbon is a key thing, and hydrogen too. And they're there, okay? So here's, you know, last year was the 150th anniversary of the Mendeleev's table of the elements. Here's a recent version of that. And all these elements, this is carbon. I put a circle around it because it's so critical. Silicon is down here, and it's also valence 4, but it doesn't allow the same complexity. And hydrogen up here. And so there's hydrogen, helium, and lithium. Those 3 came from the Big Bang. All these others came from stars, and the heavier ones come in exploding stars, or colliding neutron stars and so on. So there's a whole working out how they happen to arise. But how is carbon formed? I mean, there's a magical thing called the Hoyle resonance. Fred Hoyle, he's a brilliant English astrophysicist, cosmologist, science fiction authors, and I loved some of his stories. And this one, October the 1st, that's today, so maybe this is too late, this talk. But that's interesting. A for Andromeda, and because he's a physicist, so these aren't super crazy things like rockets shooting through space at 10 times the speed of light. This is how extraterrestrial life, extraplanet life, and the constellation of Andromeda got life to Earth by sending computer codes. But anyway, but Fred Hoyle believed in a steady state universe, as I said, same at all times. He didn't believe in the Big Bang. In fact, he coined the term Big Bang as a derogatory term, your Big Bang, you know, but it stuck. Anyway, this was a brilliant thing, this Hoyle resonance. So he asked himself in 53, how can the universe have so much carbon? How could it be made in stars? Now, helium was coming from the Big Bang, as I said, we knew that. And you have to get 3 helium together to make carbon. And it can go in steps by 2 helium colliding and forming beryllium 8, and then another helium joining it to make the carbon. But this is a quick step, and it wouldn't happen. The beryllium unstable would break up. The only way it can happen is if there is a particular feature in the carbon atom. It's called a resonance there, an excited state of the carbon nucleus. And Fred Hoyle told, he's British, but he was at Caltech, and he told Fowler, an astrophysicist, there has to be an excited state of the carbon nucleus with an internal energy, he said, of 7.68 million electron volts. And he said, if that wasn't there, then he didn't see how carbon could be formed as much as it is in the universe. And Fowler's colleague did the experiment and found that resonance exactly. In fact, Hoyle said he predicted it should be between 7.3 and 7.9 million electron volts to produce enough carbon for life to exist. And between this and this number to produce the abundance of carbon we actually observe in the universe. And the answer is this, right in between them. So that's an amazing thing. If that resonance wasn't there in the carbon nucleus, which is about the strong force between protons and neutrons, then carbon could easily not have been produced in nearly enough quantity. And it's not only the carbon story, oxygen has to have just the right energy level as well. Otherwise, it would produce more oxygen than carbon. And it only happens with very hot stars, so very hot and exploding stars, and throws the carbon into the universe. So that is sort of an amazing thing. And then another miracle, if you like, is that neutrinos, which are made in nuclear reactions in the sun, in fact, most of the nuclear reactions combining protons into deuterium in the sun produce neutrinos, which have a certain spectrum, and they can come out of the middle of the sun because neutrinos carry energy out. They travel easily through so much material. They're very hard to, so weakly interacting. And so these neutrinos, you see the numbers here, 10 to the, this is per second per square centimeter, 10 to the 9, that's a billion. There's millions of neutrinos per second going through your thumbnail, coming from the sun. They don't interact with your thumbnail. You have to have massive detectors to detect them. I show this diagram. It's another way of reactions happening in stars hotter than the sun, the Cno cycle, where you use carbon, nitrogen, and oxygen to catalyze the fusion of 4 hydrogen atoms into helium. And in the process, you spit out gamma rays and neutrinos. And I got quite excited about this reaction because these happen in the sun. And you see here an interesting reaction that caught my eye because it's a proton plus nitrogen 15 going to carbon and helium and 5 million electron volts of energy. And you can make that reaction happen in the lab with 1 million electron volt on the hydrogen into nitrogen. And it's a nuclear reaction with no radioactivity, and it produces energy more than you get out. Unfortunately, it's very inefficient because of scattering and ionization. But for a while, I thought, solve the world's energy crisis with that thing because air and water coming in and carbon and helium coming out. I still think it could be useful for electrically heating buildings with more efficiency. But anyway, that's a side story. So I show this picture because This is one of the experiments that showed these neutrinos coming from the sun. It's called Cno, the Sudbury Neutrino Observatory, an underground flask of heavy water. Heavy water's got H2O, but the hydrogen is actually deuterium. It's in this flask here, and they showed that electrons have mass, and the different types of neutrino and so on. The neutrinos have mass, sorry. So this is quite a spectacular sort of experiment. And here's another one where, as I said, the sky is emitting neutrinos. And these amazing detectors, here's in Japan, the Super Kamiokande Neutrino Detector. So it's a vast tank of ultra-pure water under a mountain, so it's shielded from cosmic rays. At the moment, the water is being filled slowly, and they've got on a little boat here, and all of these are photomultipliers. They're like large light bulbs, but instead of giving light out, they take light in and produce an electrical signal. And when this is full up with water, neutrinos come from the sun. It can most pass straight through, of course, but occasionally one will interact and produce a ring of light, which is detected in these tubes. And from the size of the ring and the position, you can tell the direction the neutrino came in. And you can actually reconstruct an image of the sun, even at night. I mean, the neutrinos come through the Earth, so that's an amazing picture. It's actually very blurry. The true sun size is much smaller than this. But these are seeing the sun at night with neutrino eyes. It's an amazing sort of thing. And now at Fermilab, we're studying neutrinos, the three types, and they change from one type to the other. And we have some very big experiments sending beams of neutrinos from Fermilab here. This is up to northern Minnesota. And there's down underground, there's a big detectors here. You see the size of the person, they're vast things. They need to be very massive to detect neutrinos because most of them go straight through. But sometimes one will hit and you will see the tracks of particles being produced. And we're trying to understand the masses of neutrinos and how they mix between each other. Here's another picture of it, this big neutrino detector. The neutrinos go 500 miles through the Earth. And the next big step is called DUNE. It's a liquid argon deep underground neutrino experiment. The next big thing from Fermilab, it's over Sanford Underground Research Facility, 800 miles away, sending beams of neutrinos through the Earth. And there's vast detectors underground full of liquid argon to detect these neutrinos, measure the type of the flavor that they are, the type that they are. So dark matter, I think probably most people have heard of dark matter. What is it? And we don't really know, but we know there's more matter there than we can see in the gas and stars and dust because it's holding galaxies together, for one thing. There was an astronomer, Vera Rubin, with her colleague Henry Ford, and she measured the rotation curves of many galaxies, and she showed that there must be more mass in there than you could account for in stars and gas and dust. A factor of 5 or so more mass than that. It's keeping galaxies from flying apart. It's also, we see it bending light gravitationally from very distant galaxies. It probably helps stars and galaxies clump together. So maybe that dark matter has a role in forming galaxies and so on, but we don't know what it is. We think it's particles that we haven't yet discovered. Perhaps it clumps into invisible worlds, or there's words now, portals to the dark sector. Maybe there are dark lumps of dark matter, even dark planets, or they're really invisible. They're not dark, they're invisible. They don't reflect light or shine light. But this is a pie chart of what we think is the matter and energy content of the universe. And this is the matter that we know. Atoms, they're made of quarks and so on. This is dark matter. We don't know what it is. And dark energy is about 75% of the universe. And that's something even more mysterious that I show on the next slide here. And I say finally, and it may be finally because dark energy seems to be blowing the universe apart. This is a cartoon showing the scale of the universe as a function of time. Presence is here. From the Big Bang, the universe expanded very fast, but it was slowing down under the gravity of all the galaxies attracting each other. But now we seem to be in a period where it's accelerating, the expansion is accelerating. And the we don't understand it. I mean, Einstein already put in his equations. He thought when he made his equations of the universe, he found that it wasn't stable, that it should be either expanding or contracting, but not stable. But he mistakenly thought it was stable, until Hubble from Wheaton claimed that actually the galaxies are blowing themselves apart. And Einstein said, damn, I could have predicted that because my equations said that it should be either expanding or contracting. Instead, he put in this so-called cosmological term to stabilize it. But now it's all come back because we know that it's not stable, but we don't know really whether in the far future it's going to collapse down to what's called a big crunch in the far future, or continue expanding, or even expand exponentially faster and faster and faster, getting more and more dilute. And then you're looking at an infinite future, if you believe infinite time, which I have a hard time believing in. So, but still, if the physics of the Big Bang have been a little different, the universe could have exploded so rapidly that no stars could form. I mean, you can imagine a universe that starts and then within what we'd call seconds or minutes or hours collapses down, and no time for stars, for galaxies to form, stars to form, planets to form, and so on. Or it could have expanded much faster straight away. And again, either expanding too fast or too slow. And there's a delicate balance between the attractive galaxy and repulsive dark energy that allowed the universe to live for billions of years, for stars to evolve, explode, planets and life to form. So all the matter we have here, apart from hydrogen, is coming from stardust, really, from exploding stars, spewing their heavy nuclei into space and reforming planets. So now let me come right back to Goldilocks again, and the planets and the Goldilocks system, because back in ancient times, up to 1781, what we knew, we had Earth, we knew that was the world, really, but we knew about planets Mercury, Venus, Mars, Jupiter, and Saturn as planets, okay. And of course we knew about the moon as well. But then Uranus was discovered in 1781, and then Neptune and Pluto, I put a question mark, I like it to be a planet, but it's small. But then since 1999, over 4,000 planets have been discovered around other stars. And this is just an artist's impression of one called Kepler 8186f. Kepler's the spacecraft that found this thing. And this is the first rocky planet that we found in what we call a habitable zone, which is a temperature allowing liquid water to have. So it's either far away from a very hot star or closer into a cooler star, but we can actually estimate the temperatures of these planets. And the idea is that if water is not essential for life, it probably makes life much easier to evolve. So this is a planet that seems to be not too hot and not too cold, but just right to allow a life. The F here means it's the fourth. When planets are found around a star, they start with B, C, D, E, and so on. So now, this is the Kepler Space Telescope out in space. So it was actually pointing in a particular direction in the galaxy, looking at a small area. Actually, I put fist here. If you hold your fist out at arm's length, that is the area of sky they looked at, and continuously monitoring 150,000 stars in that small part of the sky with this amazing digital camera, okay, and this amazing thing. And they're looking at these stars for changes in brightness. And that's how many planets were discovered, because if the planet goes in front of the star, it's orbiting, the light dips for a little while, and you measure the dip, and you can see the dip caused by the planet passing in front. And here's a graph showing the number of detections per year, cumulative detections per year. So back in 1999, it started, but now with Kepler coming in, there's many different ways of detecting these planets, but the green ones here is these transits where you see the light of the star dimming as a planet passes in front of it. And you want to see it happening more than once to confirm it, and then you've got the orbit, and you know how long it takes to go in front of the star. You can learn a lot about it. And And there are other ways, radial velocity is another way here. Now, what that is when a planet is going around a star, not only does the star pull the planet to it gravitationally, but action-reaction, the star's pulled a bit towards the planet. So the star also wobbles. So as the Earth goes around the sun, for example, once a year, the sun is doing a little wobble, balancing the gravity of the Earth, and of course all the other planets too. So it's a complex little motion, but you can sort it out, and you can find the planets there. So this is it's maybe a bit. So this is a graph showing planets that have been found by Kepler, by W First, another one, and this is the orbital axis. This is the Earth's orbit size. So there's the Earth, and this is the Earth's orbit mass, Earth's mass. One Earth mass, one Earth orbit. So Earth is here, okay? And up here you've got Jupiter and Saturn. They're much heavier, and they're further out. Of course, they've got much bigger axes. But it doesn't mean there are no planets here. It's just harder to find them when they're closer to the sun and smaller and so on. But just to give you an idea, and it seems that we can estimate that most stars have planets. Most stars in our galaxy have planets, at least in this part of the galaxy. Maybe close into the center, it's a different environment. But that is, we think that there's probably something like 100,000 million different planets in our galaxy. And as I said, it's about the same number of galaxies in the universe and neurons in your brain. So some of these stars have got a large number of planets. Here's TRAPPIST-1, which has got 7 planets, and 3 of them seem to be in the so-called Goldilocks zone. And actually, we've seen two planets in front of the star. These, of course, we can't see. We don't have this magnification, but these we know roughly the sizes of the planets. We can get the sizes of them and the temperatures of them, and this is just a sketch of how they might look if you could see them with a telescope there. And here's another beautiful artist's impression of a scene on exoplanet TRAPPIST-1F, liquid water, rocks, and so on. It's not super accurate because the other planets wouldn't be seen so big in the sky as that. But anyway, it's a nice picture. And the astronomers have got very smart at unraveling these wobbling motions of the stars. So here's an exoplanet hunter called HARPS. And it has, so it sees the stars wobbling with the planets going around it, and it unpicks their 3 planets with these different periods, and then fits them and so on. You can be very clever and fit all these things and find out the planets in the system there. So coming back to life on planets, so as I said, life as we know it requires complexity, and carbon is the only atom we know that can do that. Likely needs for life as we know it are temperature allowing liquid water somewhere. A beach would help to have gas, solid, and liquid together. Of course, we don't know exactly how this all happened on Earth, but our atmosphere was transformed by life. So one clear way in which we can see first signs of life around other planets is by studying their atmosphere. If you had less oxygen and animals can't breathe, if you had more, plants burn up. Mars and Venus have virtually no free oxygen. The first signs of life on other planets or worlds are probably measuring the atmospheres during transits in front of the sun, so in front of the star. So the light from the star can go through the planet's atmosphere, and we can detect and measure the composition. And after making these slides, there's just news these days about astronomers finding a complex molecule called phosphine in the atmosphere of Venus. And it's got quite a lot of excitement because although there's phosphine in Jupiter and Saturn, it's a different quantity and they're very different environments, and we can understand how that's made there. But in Venus, to have phosphine in the level we see it in the atmosphere, it's associated with life. Biological life on Earth does emit phosphine, and so it's very intriguing. I wouldn't say it's confirming life on Venus yet, but it's very intriguing. Here are some atmospheres. So Mars is showing a hazy, thin atmosphere. Titan, a moon of Saturn, has an atmosphere. Jupiter's got an atmosphere that's 5,000 kilometers deep. It's a very turbulent thing. And even Pluto has some sort of atmosphere backlit by the sun. So this is from the Pioneer spacecraft, or Voyager maybe, I don't know, looking back towards the sun from Pluto. So planets have atmospheres. And this is an artist's impression of a fairly nearby star, Proxima Centauri. It's only 4.2 light years away. It's one of the closest stars. It's the closest exoplanet we know. Its year is 11 days, but the star is cool, and it could have liquid water or oceans on it. And then, so this James Webb Space Telescope, which is not up yet, it's hoped to be launched next year. It's a successor to Hubble telescope, NASA, European Space Agency, and Canada together. So these big mirrors, and they're assembled in space. It's a big thing that is designed actually to study the chemical composition of atmospheres around other planets. Now, okay, how many planets in our galaxy and how many have life? Okay, so of course we don't know the answer to that. We know that it's at least one. If we call life as a complex molecule capable of self-reproduction or a template for reproduction like proteins, carbon atom is needed, we think. Let's assume that. And then there's this Drake equation that you may have heard of by Drake. So he puts down guesses, really, of what you need to have. Can you guess how many planets might have life or even intelligence, like extraterrestrial intelligence? SETI is a search for extraterrestrial intelligence by listening to radio signals. It's called a Fermi-type problem. Enrico Fermi, who one of the most brilliant physicists, and he Fermi-type problem. He said, how many piano tuners are there in Chicago? And he said, well, we can figure it out roughly, by how many houses there are, how many of them would have pianos, how often does a piano need tuning, and how many pianos can a piano tune a piano. And he worked it out, and you get within a factor of 2 or so the number of piano tuners. So this is that sort of question. So Drake put together several things, like the average rate of star formation in our galaxy. We're talking about our galaxy, and the fraction of those stars that have planets. Now, we know this is about 1. It's not far off 1. It could be a half. But, and the average number of planets that can potentially support life per star that have. And we're beginning to know these now. But these other things are really unknown. The fraction of planets that could support life that actually do develop life at some point. So, maybe there are planets that could support life, but it doesn't actually get started. We know it got started on Earth, but we don't know how possible that was. The fraction of planets of life that actually go on to develop intelligent life, because he's talking about searching for extraterrestrial intelligence using radio and so on, civilizations. The fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And all these things we just don't really know. And they could be 0, except we know that there's one that is there. But one thing I think which is very important is the length of time for which such civilizations release detectable signals into space. You see, so our Earth is about 4 billion years old, okay? And life on Earth is actually more than 3 billion years life on Earth, but we've only been capable of sending radio signals for the last 130 years or so, which is a tiny, tiny fraction. Now, will we continue to be a civilization using radio signals for another 100 years, 1,000 years, 10,000 years? I don't know. Maybe our civilization has a short life. Maybe it's natural that civilizations don't live so long, or at least don't use radio for so long. We don't know. We just know that the last 4 are not exactly 0 because we're here. This is a wonderful picture of the number of galaxies in the Hubble Ultra Deep Field. So this is the size of the moon on the sky. It's half a degree across. And I don't know if you can see it, there's a little square here. This square is zooming in, looking at this square with no stars in our galaxy. And this is the exposure of 1 million seconds, which is 12 days, with a digital camera that is, a huge area, and all these are galaxies, and that's a tiny area. So you multiply that number by that area up the whole sky, and you then figure out that yes, there are something like 100 billion planets in each of these things. So, well, but these are very old galaxies. I mean, we're seeing them as they were a long time ago. So maybe life hadn't developed on them yet. Anyway, these are all big questions. So finally, and I'm nearly at the end, but is our universe unique? Or is it just one of a vast number? And I put 10 to the 100, that's 1 with 100 zeros. Of course, I don't know anything about that number, just a very, very big. And this is an idea called the multiverse, and there are a dozen very different ideas about that, or different types of multiverse. But the basic idea is that our accessible universe, as we can see in the last picture, where you saw out to the very distant galaxies that are, in the early stages of our universe, they're so far away, and that there are others that we cannot interact with. Either they're too far away, or they're just disjoint in some completely sense, different dimensions. Of course, is this science? Can it be falsified? Generally in science, we have some ideas. If you can't falsify it, you say, well, that's maybe not science then. But if this is it, this universe that we can see and we love, it's the only one, then you have to ask, how could all those physics miracles I've talked about, the carbon, the antimatter asymmetry and so on, have come about? Now, the multiverse answer says, well, there's such a vast number, a huge number, all with different physics. So the particles have different masses, different numbers of them, the forces are different, maybe the dimensions are different, maybe three-dimensional space happens to be us, maybe it could be 4 or whatever. But then you can have nearly all of them sterile, but then some of them would have, by chance, some just right for life. And you can think of that. So you've heard of this anthropic principle and different forms of this, again, so many versions of them. Brandon Carter really made this, started this with the weak principle. It says we exist as observers, so the universe must be old enough to, and with special properties that we can exist as observers, which is true, but I don't think it really explains anything. And then there's a strong anthropic principle that goes further and drawing conclusions. And Barrow and Tipler have a book about this, and they come down with 3 forms proposed for this. 1, 2, 3. He says, one is there exists only one possible universe designed with the goal of generating and sustaining observers. This can be seen as simply the classical design argument restated in the garb of contemporary cosmology. The purpose of the universe is to give rise to intelligent life with the laws of nature and their fundamental physical constant set to ensure that life as we know it emerges and evolves. And this is a sort of design argument. And this is now becoming theology, which I can't go into much more. But a second view is observers are necessary to bring the universe into being, which is somewhat different, but and it gets a bit head around it. But and then finally, the third, an ensemble of other different universes is necessary for the existence of our universe. This is the one where you have trillions and trillions and trillions of universes. They're all different, and most of them would be sterile. But if you have so many of them, by chance, the properties like the speed of light and Planck's constant and so on, in some of them, in a tiny fraction of them are right to allow life. So we have, to our best of knowledge, our standard model of particles and forces got many different parameters, about 24. There's the speed of light, Planck's constant, the gravitational constant, these different quark and lepton masses, 12 of them. We may find a relation between them, so that might become down to one parameter. They mix between them and so on, couplings of forces, Higgs mass, dark energy, all those things. Now, if you had 2 parameters, you can plot as a point on graph paper, right? 3 parameters, you plot on a point in 3 space in a volume. And here's a volume, a cube, with 8 by 8 by 8 cells, and all these different cells could be representing different physics. Each tiny box can say a universe with different physics. But if you have 10-dimensional space instead of 3-dimensional space here, and huge numbers of regions, then every box can be have different physics, and then some could be right for life. So so here, one of the views, this is André Linde, who talks about eternal inflation, where universes pop into existence out of out of nowhere in our universe and the continuously evolving universes and so on. Perhaps there are trillions and trillions and trillions of other universes. Speculation, philosophy, it's certainly interesting to think about. This is one version of this. But I should say, and I should finish very quickly, but outstanding physicists are divided on this issue. So many argue science should restrict itself to what can be known, and others say, well, it's a legitimate area for study, even if it is always theoretical. And I don't have time to read this, but you can read it later, I think, if it goes up there. So, these are examples of the opposite arguments. Paul Davis, in an article in the New York Times, and George Edison, Scientific American, he says, contemplation is an excellent opportunity to reflect on the nature of science, the ultimate nature of existence, and why we are here. So this is food for thought. And I just had my personal version here, which is an idea. I showed this before as the universe, anti-universe pair creation. I wrote this sort of with two hypotheses. One is that space-time has no boundaries. Einstein said no space boundaries, but I said time, no infinities. And then I get this idea of time as a closed loop. The universe is a vacuum fluctuation in outer space-time. And this sketch of outer space-time, where all universes are popping into an existence out, and here again, it's closed. And this is a sort of steady state in the outer space-time. But don't take this more than it's just a warning. I mean, it's not a published idea or critique and so on. It has issues, but I like it to think about it. So what do I think about life elsewhere? We once thought the Earth was unique. That was the world. Then science came, and we showed that there are thousands of discovered planets around other stars, surely many billions of planets around the Milky Way galaxy. I think it's extremely likely that some form of life has originated on at least millions of planets. And we may know that in our lifetime. For example, life can change the atmospheres of planets, and we can see chemicals in the atmospheric composition that is likely to be generated by life. But then what are the chances of multicellular life? Because for 1 billion years, we had life on Earth, but it was single-celled. And then once it became multicellular, it started evolving to complex sentient creatures. So here, 13.7 billion years of the life of the universe, and 125 years of emitting radio telegraphy. So it's a small fraction. We know it's not zero. So we could be alone. What a responsibility if we're alone in the universe. But on the other hand, there could be a vast number. I think of life, but I'm not sure at all about civilizations, because maybe they're limited in the time, and maybe they don't last very long. We certainly have to change the way we behave if we're going to last for thousands of years, I think. So I leave you with food for deep thought. I showed many areas of physics that had to be just right for life. If there's only one universe, how did that happen? If there's a vast number of universes, all with different physics, there's a different perspective. You still don't explain how they came into existence if you need to, but is that outside the realm of science forever? I don't know, but thank you.